introduction.
Yes,
That was the most
about,
important part.
I forgot about that. Apologies. Okay, sorry.
Now we're recording.
People are not so good with the camera, but I don't know.
Yes, I think nobody followed up on my little request to turn on the camera. So if you hear me, people on Zoom, if you hear me, please turn on the camera. I'll be grateful for that. Okay, so today's topic. Let's start with a little background here. Is this the right thing to use to erase? Yeah.
Yes, there's this thing called water.
Huh?
Sometimes.
Oh, what?
Like in the old times, you use water to clean stuff. It's over.
If you wet it.
So what's better? Should I use water or just dry? What's better?
I use water, but I don't know. I never tried dry.
Okay, let's try dry, and then if it doesn't work, we'll see it. If you don't want to take my email, it's a good time because I'm going to erase it. So here's a fact about cancer. So we can look at the human population, and there's different ages here. So we can call this axis age, which we can call T in this presentation, and this has unit of years. And on this axis, we can plot the probability that somebody with this age would get cancer in that year. So this is probability of getting cancer at this or at age t. And this, we will call this P index C of t, right? So the probability of getting cancer at the age t. And what this function looks like, it looks like an elegant curve. Yes, shaped like this. Where over here we would have 85 years old. This is 50. This is 0 birth. And typically, like the risk of getting cancer at age 50, it's something like 0.01%. And if you're at age 85, you have a risk of it's like 10 times higher per year. And how is this computed, right? So just to make very clear what these numbers means, the way you compute this is that, if you look at Switzerland today, right? So in Switzerland today, there's around, if you take how many people are age 50 in Switzerland nowadays? So it's around 130,000. Look at the numbers. So it's around 130,000 people age 50. And then of those, something like 360 will get cancer this year. And so this is how you get this figure of 0.1%. Does that make sense? So seeing this, like there's a first question that directly emerges, right? So the question here would be, why would the risk of cancer increase with age, right? So clearly there's like this curve in how the risk of cancer increases. So why would that be? Like, can we think of a biological reason why this should be? And so what we're going to do now is just we're going to take 3 minutes to think about, we're going to pair up and then, just look to the person closest to you, not too close because Corona, but you guys are sitting well, perfect. So just find a neighbor and then just try to brainstorm about what are the possible causes for the cancer risk to increase with age. And so we're gonna take 3 minutes now to do that. Go. And dear Zoom people, I will break you down into rooms so you can have those discussions too. How do I do this? You guys are 6. We're gonna make 3 breakout rooms. Enjoy.
There also might be more possibilities for instances that cause previously using sound to rapidly. Long
Anyway.
If you have like a group of cells that are mutated and then you get a cut, then the cells are gonna replicate rapidly with the which increases the probability of getting another mutation. Or if you have more instances of infection or
higher mutation causing events.
yeah.
Health insurance.
Okay, so let's see. Let's close the rooms. So we're gonna have the Zoom people back in 15 seconds. And so 50 seconds we'll let's gather the ideas. 2, 1, 0. All right, here we are. We're back. So welcome back, Zoom people. Actually, can I, if you guys have a question, just shout it. I should be able to hear it, but just to test, can somebody say something, anything? Just to see if I can hear you.
Yeah,
Yes.
okay. Hello.
Perfect. All right. Thank you, Jerome. Thanks, Julie. Okay, so let's get a survey of what kind of ideas could explain why the risk of cancer increases with age. So, what is one idea that came up in the discussion?
So, we think the correlation of mutations are higher with age. The immunity is lower.
Okay, so the idea would be that as you age, immunity gets lower, and so there's more chances for cancer to start. And I didn't get the part about mutation. Could you just repeat it? I just didn't hear it acoustically.
I think the probability of getting the cancer is higher because the mutations are more accumulated with higher age.
Yeah.
And so the risks are higher, and then the immunity in older individuals are low.
Okay, great. So okay, all right. So one hypothesis is mutations accumulate with age, and second, immunity goes down with age. Great. other options that maybe emerged for the discussions?
I also thought maybe all kind of repair mechanisms are maybe not working that well anymore.
Yeah, so speaking as you're saying, as you age, or not you, but in general, as we age, the repair mechanisms lose in effectivity, and that facilitates acquiring mutations. Okay, great.
Or like if you already have mutations that they will not be fixed
Right.
anymore.
Okay, great. So repair activity. Is this big enough? I should probably write bigger because it's big enough for me, but can you see from, yeah? Goes down with age, and mutations don't get fixed. Great. That's a legit hypothesis. Any other hypothesis that's maybe thought of in discussions? Any hypothesis that maybe only emerge on Zoom? So these are all very good hypotheses, right? And since the idea is we're doing a tutorial about modeling, then it's a good thing to try to start with one hypothesis, right? Because in principle, we could look, it's a very legitimate approach to just look at all possible scenarios here. And we're just gonna have to start with one, right? Because we can't do everything at the same time. So let's start by considering this scenario, right? And really, the way we can think about this is that we could have a scenario where maybe let's keep this on, and yeah, let's do it like this. So one way in which we can think about how mutations would cause, how cancer mutations could occur, and how this change with age is, we could imagine a scenario where we have this probability. Let's call it rho. This Greek letter rho. And that's going to be the probability that the cell gets cancer mutation within 1 year. So the scenario is basically like this. There is an individual. So this is a person, and this person has many cells. And so the rho is going to be the probability that, that this cell here starts in that year, acquires the cancer mutations, and starts making more cancer cells in that year. Okay. And so the interesting thing now is, we can think about what kind of curves can we generate from this scenario, right? And we can think for this. So again, if this is age t, and this is the probability to get cancer this year, then in principle, under this model that every year, each cell has a probability to get a certain cancer mutation, then the risk of cancer should basically, it should be a line, right? It should look like this, because it's a bit like winning the lottery, right? There's, if the chance that you will win the lottery in a given year, if you play at the same frequency or independently of age, it's flat, right? There's no reason why if you're 50, you have more chances to win the lottery than if you're 20. So under this model, it's basically the same, right? That you get this mutation, that year, and then you get a curve like this. And maybe the probability of getting cancer that year is going to be something like very determined by the chance that the cell will get this cancer mutation in that year. And also this we have to multiply by the number of cells that in principle can derive to cancer, right? So we're going to have n, and this is number of cells that could start cancer. And this you can think maybe as the total number of stem cells or progenitors that, self-renewing progenitors that you have in the body, because if a cancer mutation occurs in the terminally differentiated cells, and for example, maybe at the top of the skin, I mean, pretty soon it will be anyway being shed off, right? And so it's not going to be a problem. So think of this about, this is your potentially set of the population of cells that can potentially initiate cancer. So we have a problem, right? Because this model, it doesn't really fit with getting a increasing curve. So then there's a question that emerges, right? What do we have to do? How do we would have to change this hypothesis? If cancer occurs just by getting mutations, well, how do we have to change this hypothesis to get the curve instead of a flat line? And so that's I can see you already have an idea. So let's think about this together again in pairs for another 2-3 minutes. All right, Zoom people, let's do new rooms. I'm going to put you with the same partner that you had earlier. So I hope that works for you.
How to get from the
Would be the same underneath the stuff. I would have to modify this to get an increase. I mean, basic, yes. Yeah. I don't know, well, I guess the concept of probability, segmentation, probability.
My idea is it's not enough just to have one mutation. You need increased proliferation and then tumor suppressive deletion and decrease apoptosis. You need like. And I'm not sure exactly how that would change the curve, whether it would be exponential or.
That's of course the chance to have this. The first row is 0. The third row is 6 to 3. So it increases. The chance of having at least 3 6s out of 10 rolls is with the number of rolls.
Yeah. That's good.
Well, I don't know, but we have to.
The chance of being a mutation. So it's like you need 3 6s back.
Oh, wow, fantastic.
Just enjoyed the session. And everything, but I mean, you weren't really doing mathematics. If you have like.
So in
The chance of a regular cell getting a mutation might be but then your cell is reproducing faster.
Maybe we can keep it to biology and research. It's not really talking
Very general stuff. It gets very confusing.
Or if you have a cell that already doesn't have proper repair.
Once you roll 6, this
All right, welcome back. So let's do again a survey of the kind of ideas that emerged during brainstorming number 2. How do we turn this flat line into a increasing curve? What hypothesis do we have to make there? Yeah, they seem to have an idea earlier. So what's
Yeah, our idea was, it's not enough just to have one mutation.
Yeah.
To get a tumor, you need like a increased proliferation and then like a decreased apoptosis and then like a deletion of a tumor suppressant gene. And then so you need the accumulation of like 3 or 4 mutations before you get a tumor.
right?
And then also, once you get 1 or 2 mutations, it's more likely that you're going to get like the 3rd or 4th mutation because your cell isn't working properly.
Okay, great. So there's, if I get you right, there's at least 2 ideas here. One idea is you think we should you need several mutations. Okay, and that takes time, and so maybe that can lead to an increase of the risk of cancer over time, right? Okay. Several mutations. Did I understand right? Several mutations take time.
Yeah.
And your other idea was about how the first mutation can facilitate future mutations. First mutations facilitate subsequent mutations. Is this still big enough? I'm worried. Next time if I get to visit here again, I will bring in Feldstecher. I don't know what's the word in English, like to look far away. Great, perfect. Are there possible options to turn this line into a curve? Also, Zoom people, feel free to shout in. Now I know I can hear you. So if we have no further options, I mean, this is good enough, right? So maybe I'm supposing that probably these are ideas that also emerge in other discussions. So you know what? Let's do this for the rest of the time we have together, right? So let's first start with this part, and then we'll look into that. How's that for a plan? So what's your name?
Joel.
Huh?
Joel.
Joel. Okay. So these are two ideas that Joel proposed, and before Joel, back in 1954, there were 2 people who came up with this idea as well. So it's been a while, but it's interesting to go back to those historical ideas because then we can see how they grew to be validated or not. And so I want to introduce to you Peter Armitage. Peter Armitage was born in the year 1924 in the UK, and he actually grew up before World War II. And as he came to finish his studies, he went to work in the Ministry of Supplies in the UK during the wartime, where he was working on optimizing supply problems using statistical tools. Like how do you make sure the army has enough supplies? And this is how he really started to grow as a modeler and a statistician. Peter Armitage, born 1924. And he's still with us today. He's 97. So if you like this idea, you can still go and pay him a visit. And in the year, the paper is basically from 1954. And at that time, he was a student of Richard Doyle. also from the UK, born in 1912, and who sadly passed away in 2002. And Richard Doll is quite an important character because he was an epidemiologist, trained as a doctor, but then became more like interesting statistical problems. And in particular, one thing that's famous about him is that in the 1950s, he was struck by how many more lung cancers that they found in hospitals. And their hypothesis was that probably had to do with this new material that they now have in airports called tarmac. Or also there was a strong increase in the amount of cars on the streets in those years. So he thought maybe the increased risk of cancer has to do with the cars. And to his surprise, he actually found that the increased risk of lung cancer was actually due to smoking that was so coming up in those years. And so that has quite a drastic consequence for him, because when he discovered the association between lung cancer and smoking, he actually quit smoking. So, this is a scientist that acts on his own findings. And both of them were working really at the MRC in the UK, Medical Research Council. All right, so let's just go through this idea, right? So that maybe instead of saying we need many mutations, let's just look what happens if we need 2 mutations. So what we can do now is write the probability that the scenario we're now thinking about is that there is this axis of let me get maybe the second whiteboard, that could be useful. This. So we're now thinking of this scenario, right? So to symbolize what we think is happening. There's still this axis of age, T, and this is birth. And now what you think, maybe there's 2 mutations that need to happen. So at some time, you will get a specific cell, you get the first mutation. And then later, there's at time T, you get the second mutation. And this is when cancer starts. And cancer cannot start until you get those 2 mutations. That's the hypothesis we make. So let's make a formula for what this curve should look like, right? How do you write the probability to get, what we want to know is what is the probability to get cancer at age T under this scenario? And so the way to think about it is really 2 things need to happen. So we need to get the first mutation. And the mutation, the chance that this mutation happens in a given cell in a year is rho, remember? So yeah, this is going to be equal to rho. And then you have T chances to make this happen, right? Because the mutation at any point until age T, it needs to happen. So we need to multiply rho by T. So this is the chance to get the first mutation. And then in that same cell, once we're at age T, we need to get the second mutation. And to make things simple, let's say the probability is the same, right? So this is now, you get the second mutation at age T. And finally, we need to multiply by the number of cells that in principle can give cancer. So we multiply by N. So this is now our expression for what is the risk of getting cancer at age T under the 2 mutation model. And so this we can write now as, if you just evaluate this and write it a bit more compactly, we get N or square T. And what's nice about it is that, if you go back to the plot of this is age, this is the probability to get cancer at certain age. Now, this is going to look like a straight line, right? It increases. Straight line of where this is the slope. It's going to look like this, which is good. Now I have an increase in the risk of getting cancer with age, but there's a sad fact about this, which is it's not a curve, it's a line. This is what the data suggests. And this is what, no, sorry. Yeah, this is the data is here. And this is the 2 mutations model. So it's progress, but we're still not quite there. So let's do a last discussion about what do we need to do? What could we do in order to get a curve there? So let's just take another 2 minutes about this. Let's break out. All right.
So then what I would do is what's the chance of not having mutation under 2 years? The chance of not having mutation give you normalized role. Okay. Right?
You can do this, but like this is if you do this extension of this in the region of smaller hole.
Okay, so it's because it's small, right? Because
That's right. This is a pattern. Approximation.
and then still it's getting
Yeah. Yeah.
I see.
All right.
I'm convinced that
Assuming that he's right.
no. Yeah. Said all along.
Yeah.
Why is it for mutation 2 there's only row, and for mutation 1 there's row?
Because you see, the mutation one, it can happen at any point before HT.
Yeah.
And the mutation two, it must start at HT, has to happen at here.
Okay.
Ah, right, okay, yeah, yeah.
That makes sense?
Yeah.
No, I thought that we broke the this game that
Right, he is kind of.
the chance of not having had these one minus rho. The chance of not throwing the six. Right? So that actually does have that. On the field is very weak, rho is very small. So that doesn't explain the rho.
All right, welcome back. So let's do a quick survey again about any ideas that emerged during the discussion. I mean, it may have been mentioned earlier, but it's a good time to confront ourselves with the ideas. So anything that came up that you want to share about how do we turn this damn line into a beautiful curve?
Rho needs to change with time.
Rho needs to change with time. Yeah. So to get line into curve, we can change. We can write it this way, right? Rho is a function of time. Yeah, it's great. That works. Anything else? And I want to share that there was a good question here about why this formula looks like this, why we don't multiply mutation 2 by time. And the reason is, remember that in this scenario, the mutation time can happen at any point until HT. And so therefore the probability that it happens at any point before HT is rho, which is the probability that it happens a certain year, times the HT. Then you have the probability that it happened at some point until HT. And then the second mutation has to happen exactly at HT, but because this is when cancer starts. So that's why you get rho T here and just rho for the second mutation. So one option is we can make rho dependent of time, and we're going to do this in the second part of the discussion, which because in 10 minutes we have a break. So this will look after the break. And what we're going to look into now is like what would happen if it took more. Well, maybe it takes 2 mutations to start cancers. What if it takes 3, right? So if we come back to our 2 mutation formula, maybe have you seen this symbol? This symbol it means proportional, right? So this here is basically proportional to t, so we get a straight line. So what happens now if it takes 3 mutations to start cancer? So this was like the 2 mutation model. So let's make a 3 mutation model. So in the 3 mutation model, again, we start at age 0, we go to age 3, then you get mutation 1 at some point, mutation 2 at another point, and mutation 3 here at age t. And now the probability under the 3 mutation model to get cancer at a certain age t is going to be, well, for the first mutation, we again have rho times t, right? This is for mutation 1. And the second one also has to happen at some point before ht, it doesn't matter when. So we also have rho t, that's mutation 2. And now the third mutation happens at HT, and that starts cancer. So since it's only within a certain year, you get times rho. And again, this can happen in any cancer initiating cell, N. And so the result of this product is now rho to the power of 3 times t to the power of 2 times n, which is proportional to t squared. And t squared is a curve. So we made progress here. Now, finally, we have something not only that increases with age, but it also has a curved aspect. Beautiful. How satisfying. I sense some relief in the room. And so let's, in order to make those curves comparable, it's a little, in principle, we can take this curve and overlay on top of the data here. But let's just do something that helps the comparison. Like we're going to take logarithms. Instead of working with the probability of getting cancer, we can work with the probability, the log of this probability, because we'll see it makes things easier to compare. So, if I want to compare, if I want to compute here the logarithm of the probability to get cancer at ht, well, this is going to be the log of this, right? So if you do that, like when is the last time you had to take a logarithm? Be honest, was it this year, last year, anyone past five years? Who has computed the logarithm this year? Yeah, great, awesome. Okay, so you remember that the logarithm of x to the power of a is a times logarithm of x, right? This is the so if you compute the logarithm here of this thing, we're gonna get that this is 2 times logarithm of t plus the logarithm of n rho squared to the cube. And so what's nice about this formula is that now it transforms it says that the logarithm of the probability to get cancer is basically going to be a line if you look at it as a function of logarithm of time, right? If you transform this into logarithm axis, we now get something like this. Logarithm of t. This is logarithm of the probability to get cancer at this age. And this curve now looks like this. So it has a certain intercept here. So that's, which has basically, it has to do with like, if this is 0, age 1, the intercept is basically logarithm of n rho 3. And it goes like this, and the slope here is 2. That's the prediction of the free mutation model. Now we have a problem, because if you actually look at real data from real patients, the data actually looks like this. So this is the free mutation model. And let's remove this. This is data. So, we're closer to the goal, but we're not quite there yet, because it turns out that the real data actually has a slope of 6. And maybe, given what we've done so far, it can become, maybe you have some idea already about how we can get a different slope just by changing the hypothesis a little bit. Because if you look at those formula, right, you see that when you have the 2 mutation model, the risk of cancers goes linearly with age. If you have 2 mutations, now the risk of cancer goes with the square of age. So if we keep requiring more mutations in order to initiate cancer, we can change this number here into something higher. And you see this number basically determines the slope. So we can just look at a scenario in which it takes k mutations in order to stop cancer. So let's just do that real quick. So up. So now we're going to do it's a k mutation model of cancer initiation. And under this model, the probability to get cancer at a certain age t, it's basically going to be, you want you need the first mutation 1, then you need the second one until ht, mutation 2, then you need more mutations, and then you have a term rho t for mutation k minus 1. And then finally, you have a term rho for the last mutation, where cancer really starts, times n. And so that thing is equals to rho to the power of k times n times t to the power of k minus 1. And so if you look at this in terms of the logarithm of the probability to get cancer, logarithm to get cancer at ht, this is now going to be k minus 1 times logarithm of t plus logarithm of n to the power of rho k. And so now, maybe let's take a new color, because this is not 1954 anymore, we have colors. Let's, so this model here can now give something that has the right slope. K mutation model with k equals, if the slope is 6, and here our slope is k minus 1. This is our slope. So if this has to be 6, basically k has to be 7, right? So it's like under a model in which 7 mutations need to start so that cancer initiates, you can reconcile the hypothesis with the data. Okay, so here the scenario is really that it takes 7 mutations to start cancer, and if that happens, then you can explain why the risk of cancer changes with age. And one interesting thing about this is that so this is the slope that's predicted by the model, right? So we see that the more mutations are necessary, the steeper is going to be the rise of cancer with age. And another thing that the model explains is, you know, what is this intercept here, right? So this term here, that's your intercept, and it tells you basically the basal risk of cancer. And so here we see that the more cells you have in the body that can in principle stop cancer, then the higher is going to be your basal risk of cancer. So bigger people should get more cancer. That's one prediction of the model. Another prediction is that if the chance of initiating, of getting those bad mutations in the cell is bigger, then also this will increase the basal risk of cancer. But none of this will change how quickly the risk of cancer increases with age. It just changes what is your starting point. So I just want to illustrate this because thanks to this model, we can now, just by looking at this curve, we can read into what are the hypotheses that in terms of cancer initiation that is consistent with the data, right? Like the shape of the data now has a concrete meaning in terms of initiation of cancer. So sadly, we still have some problems here, right? Because like 7 mutations to start cancer, and that doesn't really fit with what we know of cancer biology nowadays. So we still need to make some work on this model. Although, you know, if you look at, what should I say? No, let's just stop here. So we have a problem. Yeah, these models suggest that it takes 7 mutations to stop cancer. And that's not very much in alignment with what we know about tumor biology nowadays, because you know, we can take some normal cells and then we can add mutations, and then it doesn't take, usually we wouldn't need necessarily 7 mutations to turn this cell into a cancer cells. And also if you look at patients, the kind of mutations that many cancer patients have over and over again, it's not, 7 is a lot, like the number would be closer to 3, something like this, which you were suggested earlier. So after the break, we'll see what we can do in order to fix this. And we're going to look into the hypothesis that once you get a cancer mutation, it makes it easier to acquire new ones. So let's take a 15-minute break.
Yeah, that's the usual, but it's up to you.
When do we have to finish? At 10?
We have to finish at 10 at the latest, yeah.
So that will work. 15 minutes. We are back here at 9:30. Pause the recording. All right, welcome back from the break. And so, you know, let's start like in any good series that, you know, Netflix series, right? So we do a recap of what we just saw, right? So we had this mystery that we started with, which is that the risk of cancer increases with age as a beautiful curve. And we wonder, how can we connect the cancer initiation mechanisms of mutation accumulation to the shape of this curve? And we did that in the final model, K-mutation model here, to find that the chance of getting cancer as a function of age increases with slope K-1, where K is the number of mutations that it takes to initiate cancer. And you have an intercept here, which we will not care so much about anymore, but it's interesting to have it because it tells you how to relate cancer initiation parameters to data that you observe in patients. Now, the problem we still have is that this K mutation model predicts that it takes 7 mutations to that cancer, and that doesn't fit with state-of-the-art cancer biology. So let's make this model a little more realistic now, right? So there was this idea earlier that you guys had that once you get a cancer mutation, maybe it helps the initiating cells to expand, and because it expands, now there are more chances that the cancer mutation will occur in the cell with the right first mutation, right? And so let's just add this to the model now and see how it changes the slope. So the model we will think of now is that each mutation confers a growth benefit, which then increases the probability of getting the next mutation. And this is an idea that was proposed by a little after let's write them on the other board. Where are you? Oh, it's here. So let's add another character, Mr. Fisher, American, who in a paper in 1958 in Nature, it's a 1.5-page paper without any supplementary material. There's no methods, so it was a bit easier to publish in Nature back in those days. But he studied this scenario, right? So, and basically it goes like this. There we go. So let's keep this on for reference, and let's remove this. We don't need that anymore. It's just a stepping stone for us to get to the K mutation model. All right. So what's the timeline of our new model? So now we're in a situation where, again, this is going to be age. Let's just note this as age. This is 0. And on the y-axis, we can plot the number of pre-cancer cells. Number of pre-cancer cells. And so in the beginning, there is 0. And then at some point in time, which we will call the tau 1, the first mutation occurs in a cell that could initiate cancer. So we go from 0 here, then to 1. So here we get mutation 1. And because of this, so far what we've assumed is basically this, right? And then you get mutation 2, 3, and so on. But now let's make a new scenario. That now, because this cell has the first mutation, it will grow over time. Okay. And so at some point, you get cancer starts. Maybe, okay. So the scenario we really have is that, at tau 1, it's just get the first cancer cells, right? Here, there's no cancer cells. Here you get the first cancer cells, and then these cells will grow. And that's, now we have to make some hypotheses about how this growth will happen, right? Otherwise, we cannot update the formula. So there's many hypotheses we can make there, right? There's so-called growth laws of cancer that we could use and plug in here. And I'm just going to explore the one that Fisher proposed, which is that initially, when the cancers, when in real tumors, those are 3D entities, they're big, they're complicated. But initially, it's just one cell, and then it divides. And initially, those cancer cells don't really have the ability to like, for example, if it's epithelial cancer, right, like breast cancer, skin cancer, colorectal cancer, really those cells are living in a 2D environment, right, because they're embedded in some surface, an epithelium that separates the inside from the outside of the body. So initially, the growth is really 2-dimensional. And you can think about how quickly that two-dimensional growth patch of precancer clones increases with time. So let's call this, you can just have this patch, assume that it's a circle because it's a reasonable assumption to make. There's no reason why it should grow in a specific direction. And we have to think about how this increases with time. And so, depending on the cancer type you study, maybe you see slightly different things, but let's, there's data that suggests that that R grows linearly with time. So you just have this two-dimensional patch of precancer cells, and the radius of it grows linearly with time. So this is time. This is the radius of this patch, and something like this. Okay. And so, this is not really time, right? This is t minus the moment where you get the previous mutation. Right? Does that make sense? And so what we want to compute out of this is how many precancers we have here, right? So let's call this n. So we now actually want to write n as a function of time. Actually, of time since the first mutation happens. And so, if we have an object like this, right? So the area of this thing, we can write as, it's the area of a disk, right? So it's pi to r squared. And we know that the radius goes linearly with time. So this is going to be proportional to, t minus 1 squared. And if you know the surface, what is the surface of the cancer cells? What is the typical size of the cancer cells? Then you can divide this area by the surface of the cancer cells, and you'll have some idea about how many cancer cells are in this growth patch. Right? So because of this, what's going to happen is that the number of cancer cells that you will get at this time here, it will be something that's proportional to time squared. Right? So I'll just write this function, this proportionality constant as beta. We don't have to think. Maybe something that we can measure. It doesn't matter for this discussion. All right, so let's keep this important finding. And now that we established this, let's now update our formula. So I'm thinking we're going to do this on the other board. Should I put this? Maybe let's put this here. So we're in this part now, right? The first mutation facilitates subsequent ones. All right. So the course of cancer initiation that we have now, looks a bit like this. So remember, if mutation 1 gives no growth advantage, then the cancer initiation diagram looks like this, right? This is age, and this is 0. This is tau 1. This is t. And so our formula for the probability that you start cancer at age t is going to be it's going to look a bit like something like this: O times 1 times tau 1, and then this point yes times it looks like this. So it will look like something like this. Should I say that 1 second. Yeah, so here I'm writing the probability that you get cancer at this time t, and the scenario is that there's a first mutation that happens at some point here. And then the second mutation will happen at some point here. And in this case, there's no advantage in getting the first mutation, it doesn't facilitate the second one, right? It's just the previous formula we wrote. But now what happens if the first mutation gives you a growth advantage, then you have to update this, right? So if mutation 1 gives a growth advantage, then we have to change this formula slightly. So the first term doesn't change, right? It's still, you still have tau 1 years to get the first mutation, but the second one now is going to be facilitated, right? Because it's going to be this rho, but this can now happen in many cells, right? Because you're, instead of happening in this cell, now it can, there's n times more chance that you can start the cancer because there's n cells at this point. So instead of writing this, now we can just write how many cells we have. And this number, we know what it's like, right? This thing is beta times t minus tau 1 squared, right? We computed it. Get it here. And so now what we can do is just do the same, but for k mutations, right? It's going to be the same idea. So let's do this for k mutations. So for k mutations, we have to change this diagram here. So the scenario would be like this. I'm running out of space a little bit here. It's a bit annoying. Let's get rid of this. So for k mutations, we have a scenario like this page, and this time you get mutation 1, you get this point, and then here you get mutation 2 at this point, and then maybe you get mutation 3 at this point, and so on and so on, right? We say we have k mutations. And so at some point we get, the mutation 3 minus 1, and get that mutation at HT, and this is when cancer starts. So let's write the formula for this scenario. And so as usual, we have initially like n cells in which you can start cancer. So we always have this big N multiplier. And then the first mutation is going to happen, at some point in this time range. So rho times tau 1. And then the second mutation, we can do this within what we did here, right? The second mutation will happen around this time, but because it was facilitated by the first mutation, there's now more chances it will happen because the first clone was growing. So we can write the second mutations here as rho times t minus tau 1 squared. So this is for mutation 1. This is for mutation 2. And then for mutation 3, well, we will start with this clone, and this clone will also make its own patch. So again, we have the same kind of term, but for mutation 3. So here we have rho times, sorry, tau 2 here, because mutation 2 will happen here in this interval. So mutation 3 will happen at some point here. So it's tau 3 minus time to tau 2 square. this is fermentation free, and so on and so forth, until we get to mutation K, which is going to be this same term here, tau minus tk minus 1 square. That's a formula that corresponds to the scenario.
Can I ask a question?
Yeah.
So why doesn't this scale, like each element, each mutation, why doesn't this scale also proportion with the time we? So before we had t times t, right?
Right.
For each element. So
Yeah.
here it seems like the times t is only applied for the first mutation, but not for the following ones. Because beta times t, well, delta tau to the power squared is just the number of cells. It's not the time that has passed during which.
Right. Yeah. I mean, normally yeah.
Or is that not higher?
Yeah. Yeah. I get the argument. Like you're saying, this is the number of cells that this is related to the number of cells that could initiate cancer. But normally there should also be an aspect about how much time has passed and how many cells were in there and so on, right?
Yeah, yes, and probably some, yeah. I don't know.
Yeah, so I mean, what I want to point out here is that normally, you know, if you want to do this computation precisely, it's we have to take into account that you don't really know it, you know, that in the end we just want a formula for what's the chance that you get all these mutations by time t, right? And so what we normally have to do is we know that those times exist, but we don't know exactly when it happens. It doesn't matter. The point is just that they have to happen. So the computation is actually more complicated, right? We have to integrate over all the possible ways that you can shift those times around. And what I'm doing here is just doing like an approximate formula for this phenomenon. So, you know, it's a slightly hand waving compared to the formula I wrote before. But the intuition holds. It's the same phenomenon, right? That if you have cells growing in a patch and the patch grows linearly with time in size, then there's going to be like a increase to the square of the number of cells that can start mutation. But I grant you that, you know, this is not like what should I say? It's in terms of accuracy, we can write a better formula.
That was not my point.
But this captures the intuition.
Follow the argument, but then I
Yeah.
follow. So this is
Yeah.
this is not a miss. That's all.
Yeah.
Why doesn't the mutation to mutation three, they don't have the probability of the mutation? Like,
Oh, thank you. Yeah, I forgot that. Yeah, you're exactly right. I missed this. Maybe I should have gone earlier to bed last night. Yes, better. Yeah, thanks for that. That's exactly right. And so, you know, just like to expand on the discussion we just had, right? So normally we would have to, you know, to look at these computations, we would have to look at all possible ways you can move those taus around. But to keep things simple, we can make the argument now that you know, if this happens in the step of 1 year, then the taus have to be in the scale of months, right? And if this happens in this case of 100 years, then the tau is probably more in the scale of decades. So what you can see is basically that, you know, those taus, it's a lot of numbers, but really they have to be scaling with time, with the total age in the end, times some proportionality constant. So what we can really write here is you know, that this thing, you know, it has to be proportional to time somehow, right? Because this sets the whole scale of time scale of this phenomenon. So this is going to be related to linearly to time, and this is going to be related to time square, and this is also going to be related to proportional to time square, and so on. And so because of this, in the end, you know, we can approximately write this as something that's going to be proportional to, you know, we just can count how many what's the exponent of the time if you do this whole thing together, right? So there's one time here. So you get 1 plus, and how many terms do we have here? Well, we have k minus 1, right? So we get something like 2 times square, k minus 1 time. And so in general, what we get in the end is really that we get that the risk of cancer will scale with t to the power of 2k minus 1. I should write this big. Probability of cancer as a function of time will scale with t to the power of 2k minus 1. So this is under this growth model that each clone starts to grow and then next mutation easier to apply. And so this is now our slope, right? If you go to log scale again, log PCT, probably to get cancer this year, this is going to be something like 2k minus 1 times the logarithm of the age plus, you know, some intercept, which okay, and let's not update it because anyway we weren't too careful about what the constants were. But essentially our new formula will look like something like this, where this is your new slope. And so now, if the slope is, we know from the data, right, that the slope is 6. So the implication under this model is that if the slope is 6, this has to be equal to 2k minus 1. And therefore, under this model, we think that we have like something like it takes 3 to 4 mutations to start cancer. And this is because in terms of the risk of starting cancer every year, before we had here just k minus 1, right? If you don't have that the clone expands and makes the next mutation easier, we just had k minus 1. Now we have 2k minus 1. So it's like every mutation counts double. Because it counts for itself, for the cell, it also counts for all the clones that it's going to start to create, increasing the risk of cancer. And so that's now satisfying, right? Because we're in a situation in which we have better agreement with biology. Because what biology tells us now, you know, if you look, for example, at this paper by Vogelstein and Kinsler, they had a review in 2015 in the New England Journal of Medicine. And what they propose is that in many epithelial cancers, you actually, it takes three mutations. Because you just have to start with, you know, what they think that they call breakthrough. And then you need to have an expansion, which is this process of, you know, the clone growing that we drew here. Where is it? Right. So that would be the breakthrough is this first step, the first mutation. This is, in other than the second mutation allows you to expand further. And then the last mutations allow you to invade and grow out of this two-dimensional object. And so this is now the end of our journey, because, or I hear, is there a question maybe? I heard a noise in the room. Who is the culprit? No, before I conclude, if you want to ask something, it's fine. We have 5 minutes, so. So if there's no further question, let me conclude here what we've done, right? So what we've done today is to see how we can reconciliate hypothesis with data, right? And we formulate this hypothesis in a stepwise fashion. We wanted to figure out, well, can we somehow connect the process of multi-step carcinogenesis with the increased risk of cancer that is observed in real patients? And what we found basically is that if you make the hypothesis that it takes 3 or 4 mutations to get cancer, and if each mutations makes the next one easier to appear because it creates clones that can expand and facilitate the next mutation, then you can explain how the risk of cancer increases with age. So that's one thing we've done today. But what's the meaning of this? I mean, to me, it's really that like the point of doing all this for me was to illustrate, you know, what's the process of formulating models and using models to reason about biomedical data. Because what you've seen is that we start with the guess, right? And then there's maybe mutations have something to do with it, with the risk of cancer. And then once you try to write the math and think through it, you see that it's not necessarily trivial to get the right shape. It's not necessarily trivial to make hypotheses fit with data. And this is why mathematics is helpful, because it forces you to write down the steps of your reasoning, and then it gives you a specific formula about how you connect your hypothesis to the actual data. So it was like, it's a crutches that helps you think about how to connect hypothesis to data. And as you've seen, the way we've done it was by trial and error, right? So you take guesses, and then it gives you some resulting model with some prediction, and then see it doesn't fit with the data, and then you have to make a new guess, see if it helps, and so on and so forth. And this is a process that maybe can take months, right? Typically, or maybe years. And here we did it in an hour, because we always went for the correct guess directly, and we simplified the formulas as much as possible. But really, the essence of doing mathematical theory in biomedical research is pretty much what we've done today. So I hope I could give you an intuition about how, well, you know, how this school of modeling or thinking works, and you know, maybe you want to do this yourself someday, or if not, then at least you know how theoreticians like to think about research. So then you have a good way, you know, to connect with them if you see a question in data that seems amenable to this kind of reasoning and work. Yeah, Joel?
I have one question. When you're developing a model like this and you're trying to like make a model that fits data, isn't it highly likely that you end up making a model that by accident fits the data, that looks like it fits the data, but doesn't actually fits the data because of the amount of data you have? Like, we could make a million different equations that would fit the graph that aren't necessarily correct.
Yeah. Yeah, that's a great point. So you're saying we now have one model that matches the data about how the risk of cancer increases with age. And can we make other ones, right? Because what we haven't explored is other ideas that you had in the beginning, right? With, for example, maybe immunity decreases, maybe the risk of, maybe the efficiency of DNA repair decreases with time and so on, right? We haven't have here. So maybe that can also explain how risk of cancer increases with age. Why do we go for this model? Is that the question?
Or could this model even be like hypothetically, what if cancer has nothing to do with mutations and we just happen to make a model by thinking about mutations that fit the data when really it doesn't?
Yeah. Yeah, I mean, that, you know, that's part of the process, right? So once you get to this formula, then this gives you ways to test the model directly, right? Because as you've seen, like maybe you remember, but we had some formula for the intercept. Like, first of all, one thing you can do is, you know, this kind of reasoning then prompted new experiments, right? To see how many mutations does it take to start the cancer. And then when you looked at pediatric cancer, you see it takes less mutations, and that prompted the idea that maybe there's some pre-genetic defects that facilitate the emergence of cancer, and that's why it takes less mutations to then initiate cancer. So it initiated new ideas. So it was a way to stimulate new ideas in the field of cancer. So in this way, it was cool. But also a good model gives you tools for its own to falsify it, right? Because maybe we had the formula for the intercept earlier. Where is that? It was on the back. There, right? So we haven't talked about this at all, right? But principally, you can start to look at this, right? So if you have some numbers about what is the population of stem cells in the body, does it fit with the intercept? If we have some number about the number of mutations, how they accumulate over time in cells, given the rate of DNA replication error at some point, can we reconcile this with this? And there's a target size in the genome of where the mutations can happen and start cancer. So if you have some idea about this, can we reconcile it with this number? And so you can see if things fit together. And the outcome of this whole process is that you have like a coherent hypothesis that matches with as much as possible as the data. And to me, this is the best you can do in the scientific approach, right? There could be other hypotheses, and then maybe you want to explore them mathematically as well. And in the end, you want to converge on something that integrates the different data sets into a common formula. And then you've done a good job as a scientist in explaining the different facets of your phenomenon in a coherent framework. Does that make sense?
Yeah.
Yeah. And we're slightly over time, so I suggest maybe that we stop here. And if there's any questions that you want to raise or any discussion that you want to have, I'm going to be around the rest of the day, so happy to talk to you. Bye-bye, Zoom people. Thanks for joining.
Thank you. Bye.
Bye.